Okay, so in the last lecture we had proved the Holder's inequality. In this particular lecture we are gonna move on with proving the Minkowski inequality, which was our main goal, right? Minkowski inequality. So what was the Minkowski inequality like? So it was like norm of x plus y p norm is less than equals to norm p norm of x plus p norm of y. Or we can write it like this: summation I equals to 1 to n mod of xi plus yi to the power p whole to the power 1 over p x less than equals to summation I equals to 1 to n mod of xi to the power p whole to the power 1 over p plus summation I equals to 1 to n mod of yi to the power p whole to the power 1 over, right? So now we will prove this. So proof. So in the left hand side we have this. So summation I equals to 1 to n mod of xi plus yi to the power p whole to the power 1 over, right? We do one thing, we just leave this 1 over p exponent for the time being. Okay, yeah, so we have this, and this we can write like summation I equals to 1 to n mod of xi plus yi times mod of xi plus yi to the power p minus 1, and this can be separated using the triangle inequality. So this is less than equals to summation I equals to 1 to n, this is mod of xi plus mod of yi, so we can distribute. So this is mod of xi times mod of xi plus yi to the power p minus 1 plus summation I equals to 1 to n mod of yi times mod of xi plus yi to the power p minus 1. Now see, we have two separate product of non-negative terms, right? This one, this is one, and this is one. So we can use the Holder's inequality in this case. Holder's inequality in this case. Holder's inequality was first norm of xy is less than equals to pth norm of x and into pth norm of y. So we can use that at this moment, right? So using Holder's inequality, qth term of y was not pth term of y. Holder's inequality was xy1 less than equals to pth norm of x times qth norm of y, right? Got it? So using this in this case, for each individual pair we get, so this can be written less than equals to summation I equals to 1 to n mod of xi to the power p whole to the power 1 over p times summation I equals to 1 to n mod of xi plus yi p minus 1 to the power q, right? So this can be written as p minus 1 times q and whole to the power 1 over q, right? This is what we have. Plus the same thing goes here. So it is summation I equals to 1 to n mod of yi to the power p whole to the power 1 over p times summation I equals to 1 to n xi plus yi to the power p minus 1 times q whole to the power 1 over q. Okay, so we have got this particular thing. now 1 over p plus 1 over q equals to 1, which implies p plus q equals to pq, which implies if I take p here and take p common, or rather if I take q here and take q common, so I get q times p minus 1 is equals to, right? So we can put it here, right? So this is less than equals to summation I equals to 1 to n mod of xi to the power p whole to the power 1 over p times summation I equals to 1 to n mod of xi plus yi to the power p and whole to the power 1 over q, right? And plus you have summation I equals to 1 to n mod of y to the power p whole to the power 1 over p times summation I equals to 1 to n xi plus yi to the power p whole to the power 1 over p, right? This is what we do. This way. Now we do one thing. Now we divide both the sides with this. Okay. So we can have like this. So summation I equals to 1 to n mod of xi plus yi to the power p whole to the power. So if I divide using this, what will I have? 1 minus 1 over q, right? Right? This is what I have. And which is less than equals to summation I equals to 1 to n mod of xi to the power p whole to the power 1 over p, and here I have plus summation I equals to 1 to n mod of yi to the power p whole to the power 1 over p, right? And what is 1 minus 1 over q? It is 1 by p. So we have thus proved the statement I equals to 1 to n mod of xi plus yi to the power p whole to the power 1 over p is less than equals to summation I equals to 1 to n mod of xi to the power p whole to the power 1 by p plus summation I equals to 1 to n mod of yi to the power p whole to the power 1 by p. So basically we have proved the Minkowski inequality. So thus what we are trying to prove is that p norm of x plus y is less than equals to p norm of x plus p norm of y, which basically implies this function is a norm indeed, So we can define, in RL we can define d of xy, dp of xy rather, equals to norm of y minus x, which norm? P norm of y minus x. Okay, got it? Now, so we can also find cases of this. So we can define the first metric. Okay, so it will be the norm this, and what is this? This is the summation I equals to 1 to n yi minus xi mod, right? Okay. Or we can generalize this, that is dp xy can be written as summation I equals to 1 to n. So norm of y minus x is our definition, right? So we have the definition of norm of x, so just putting y minus x in place of x, we are done, right? So we can write it as the mod of yi minus xi right to the power p whole to the power 1 over p. Got it? Clear? And so this is when 1 less than equals to p less than infinity. and else it is max I equals to 1 to n mod of yi minus xi p equals to infinity. Okay. This is the metric definition. Okay. If you put p equals to 2, then it's called the Euclidean metric. Okay. If you put p equals to 2, then you get Euclidean metric. Okay. Putting, so rather you can say it like this. So d2 of xy, which will look like this, summation I equals to 1 to n mod of yi minus xi squared and the root over of the whole thing. Okay, this is called the Euclidean metric. Euclidean metric or Euclidean distance also. Euclidean distance. Okay. Okay, and this function is called the Euclidean norm. It's called the Euclidean norm. Okay, these things are clear. Now similar norms can be seen in the n-dimensional complex space also. Okay, this is an observation and a simple conclusion. Okay. So what I was trying to say is that, it's like Rn with the Pth norm and Cn Pth norm are normed linear spaces, hence metric space. And the metric definition I have already given. Right? Clear? Okay. Next we move on to our next concept, which is regarding sequence spaces. I'm giving a brief, statement about sequence spaces is that if you take a set of sequences which obey certain conditions and that set comes out to be a vector space, then we say such sets to be sequence spaces. For example, we have a set named L1. Okay. So it is basically a set of all those sequences such that mod of xn converges. The sequence given by mod of xn converges. Clear? So suppose we take a set of sequences. Okay. And in a similar way as we just did, we try to define a norm on the set of sequences and check whether it is a defined norm or not. Okay. So we take the p norm of elements taken from this sequence, let's say. Okay. And it comes out to be x is a sequence. Yeah, x is a sequence. And we take the norm of the sequence. Basically, x is belong to C. Writing it like this. I use the term incorrectly. X is not a set of sequences. X is a sequence. So, okay. Suppose we have a set of sequences. Okay, and x is an element of this. Clear? Now we can define the norm. So where x is this sequence. Yeah. So we have p norm of x. We similarly define p norm of x as the summation. In this case, as we are taking a sequence, what we take is that from the summation from I to infinity, 1 to infinity, right? Mod of xi whole to the power, mod of xi to the power p whole to the power 1 over p. This is when 1 less than equals to p less than infinity. And here, since there are infinite elements in the sequence and we cannot define the maximum here, we take the supremum. We take the supremum over I. okay, of the elements xi. So p equals to, okay, or we might not use the mod here as we are taking the supremum. Got it? Also to be kept in mind that this definition only appears for convergent sequences and bounded sequences. This norm definition can only be applied for convergent and bounded sequences. Okay. Now to understand this better, we choose a particular set to understand it, or rather we define a particular set to understand it, which is LP, and it is the set of all those sequences such that norm of p norm of x converges. Okay, clear? Clear? Got it? Okay. In a similar way, we can define L infinity, which is the set of all bounded sequences. Set of all bounded sequences. And it is very much trivial that this is a vector space. It is very much trivial that this is a vector space. Okay. Also, by the definition of convergence series, by the definition of convergence sequences, we can obviously say that for all p, okay, be it 1 less than equals to p less than infinity or p being infinity, LP is a vector space. Okay, because sum of two convergent sequences is still convergent, a scalar multiple of a convergent sequence is still convergent. And in case of supremum, okay, so the sum of the supremums gives a new supremum of the added sequence, and if you take the scalar multiple, the supremum scales by the same multiple. Okay, so these two cases are pretty much similar, pretty much trivial, I may say. Okay, so basically what you need to prove is now whether the triangle inequality with the help of this norm is obeyed in this particular space or not. And if so, then we can say that this set LP, this vector space LP, is a non-linear space, which will eventually indicate towards the fact that this is a metric space indeed. Okay, so again we need to check for the triangle inequality. In very simple sense, what happens is that when you need to check whether some particular set, some particular vector space rather, is a non-linear space or not, and you are given a norm, what happens is you need to basically check for the triangle inequality, because the other two properties which a non-linear space must obey, they pretty much gets obeyed due to the fact that it's a vector space and the function given is a norm. Okay, so triangle inequality is the main thing which you need to check first, the main concern. Okay, so the triangle inequality, and this is also called the Minkowski inequality. Okay, this is also called the Minkowski inequality. It is called the series form. Okay, so the triangle inequality is pth norm of x plus y is less than equals to pth norm of x plus pth norm of y. Right, or we can write it like this: summation I equals to 1 to infinity mod of xi plus yi to the power p whole to the power 1 over p is less than equals to summation I equals to 1 to infinity mod of xi to the power p whole to the power 1 over p plus summation I equals to 1 to infinity mod of yi to the power p whole to the power 1 over. Right, this is also called the Minkowski inequality. Minkowski inequality. It is called the series form. Okay, So proving this is what we had already proved in very simple sense. Okay, for example, now see, convergence or properties related to infinite series is basically based on taking the partial sums, right? Convergence and other properties are basically related to taking the partial sums. So if we take a partial sum which is finite, which is obviously finite from considering, let's say, partial sum as n terms, and we can imply the Minkowski inequality which we have already proved on the partial sums, and then we take the its tending character, that is it tends to some value as it converges, because I have already said that this definition only is obeyed for by convergence sequences. So we take the concepts with partial sums, we check whether it obeys the Minkowski inequality, then we apply limit, and on applying limit we get what we need for this infinite series, right? For the sequence, that is what we do is that we take the partial sums. Let Sn equals to summation I equals to 1 to n mod of xi plus yi to the power p, un equals to summation I equals to 1 to n mod of xi to the power p, and vn equals to summation I equals to 1 to n mod of yi to the power p. Now see, so we have taken these into considerations, and we say Sn tends to S, obviously as n tends to infinity, or un converges to u, Sn converges to S, un converges to u, and Vn converges to V. Okay, so basically these three are the sums which we have in case of the Minkowski inequality in series form, and these ones are the form which we had in the pth norm of the Rn dimensional space, right, which we have already proved in the first proof of the Minkowski inequality. Now see, previously we had that Sn to the power 1 over p is less than equals to un to the power 1 over p plus vn to the power 1 over p. We have already proved it. We have already proved it. Okay. We have already proved it. Now see, from here you can say one thing. From here you can say one thing, that this statement basically implies that LP is a vector space. Very simple sense. So see, yeah, from here you have Sn is less than equals to un to the power 1 over p plus vn to the power 1 over p whole to the power p, which implies Sn is bounded, which implies Sn is convergent. Sn is convergent, which implies that, see, this was convergent, this was convergent. Basically, we tried to prove that LP is a vector space. So we took this to be convergent, this to be convergent. Basically, what we did is that we take xy from LP. So this is a convergence series, this is a convergence series. Then we try to prove x plus y belongs to LP. So we need to prove this is a convergence series, which we have done here. So which implies x plus y belongs to LP, which implies LP is a vector space. Okay, simple sense. Because I directly wrote vector space because the scalar multiple case, it is very much clear. Okay, so this much is done, and also we have Sn to the power 1 over p is less than equals to un to the power 1 over p plus vn to the power 1 over p, and so since Sn converges to S, un converges to u, vn converges to v, so we can write it as S to the power 1 over p is less than equals to u to the power 1 over p plus v to the power 1 over p, which is our required Minkowski inequality. Okay. So from here what we can say that LP is a non-linear space, right? Implying to the fact a metric space. And here also we can define the metric similarly. I don't think I need to do it again, or rather I will do it. Okay, so in case of LP, the metric must seem like a norm of y minus x, sorry yi y minus x supremum over yi minus x, right? Right. So this can be written as summation I equals to 1 to infinity mod of yi minus xi to the power p whole to the power 1 over p. This is for 1 less than equals to p less than infinity, and this is for p equals to a matrix space. Yes. Now let's check a few subspaces of the non-linear space. Let's see. Okay, so we already have a few definitions like L1, what is LP, what is L infinity. These are definitions we already have. Suppose I take x to be the sequence 1, 1 over 2, 1 over 3 and so on. Okay. Now what is L? L1? L1 is the set of all those sequences such that summation I equals to 1 to infinity mod of xn converges, right? But we know already that this sequence does not converge. This series does not converge. Okay, so we can obviously say that x does not belongs to L1, but it is a bounded series. X is a bounded sequence, which implies x belongs to L infinity, right? X belongs to L infinity, right? Also you may see that x belongs to L square, because 1 plus 1 over 2 square plus 1 over 3 square and so on, this series converges. Okay, so this was an example that a sequence which does not belong to L1 belongs to L infinity and belongs to L2. Okay, so we will use these things to understand the subspaces of L infinity. Okay, so we will check the concepts of subspaces of L infinity. Okay, so the first among them we take C, small c rather, small c. So this is the set of all convergent sequences. Set of all convergent sequences. Okay, and it's also a vector space. So since it is the set of all convergent sequences, we can obviously say that C is contained in not equals to L infinity. Right? Every bounded sequence, must not be convergent. May not be convergent. We have just seen in the previous example. Okay, x equals to 1, 1 over 2, 1 over 3 and so on. It was a bounded sequence, but it was not a convergent sequence. Okay. Next definition we have, let's say C0. It is the set of all convergent sequences converging to 0. Okay, that is the set of all converging sequences such that limit n tends to infinity. Okay. Now this is the set of all convergent sequences, and this is set of all convergent sequences converging to 0. So obviously C0 will be contained in C, which is contained in not equals to L infinity. Now here also is strict containment. Okay, not equals, strict containment. Okay. Because it is kind of trivial that every convergent sequence might not converge to 0, right? Obviously. Is this much clear? This much clear. Now see. Now see. Now if we talk about LP. Okay, if we talk about LP. So what was LP? LP was the set of all those sequences such that summation I equals to 1 to n xi to the power p converges. Okay. Okay. So this is just a simple case of C0, a special case of C0. Okay, we might say, because if limit n tends to infinity xn equals to 0, then xi to the power p, this summation will also converge, right? Or rather, I can say it like this: if this statement appears, then C0 is bound to appear. Okay, but this is not mandatory to take place all the time. Okay, so what I'm trying to say is that LP is contained in not equals to C0, which is indeed contained in not equal to C, and is contained in not equal to infinity. Okay, this thing happens because the sequence which you have just taken 1 over 2, 1 over 3, and so on. L2 was converging to 0 as well, right? But sorry, it was a converging sequence, not converging to 0. It was a converging sequence, but it was not in C0. Okay. Okay. Rather, did I say something? Oh, sorry. My bad. So this was in C0. This particular thing was in C0. Set of all converging sequences converging to 0. Yeah. Right. Got it. LP cannot be equal to C0. Got it. Okay. So this basically deals with the strict containment. Okay. And next we have another definition, which is the set of all sequences such that xn equals to 0 for all n belonging to n minus e, where e is a finite subset of A. Basically, what I mean to say is there are infinite zero elements in the sequence. C00 is there are infinite zero elements in the sequence. Okay, the infinite zero elements in the sequence, and this C00 contained in equals to LP. Okay. So it is an exercise to find why it is a strict containment, and an example which belongs to this but does not belong to this. Okay. Okay, so let's move on to the next topic. Okay, the next topic we have is function spaces. Okay, function spaces. Yeah, so let us take a non-empty set. Let E be a non-empty set, and we define the function space as BE. It is a set of all bounded mappings from E to R. Okay. 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 We also define the infinite norm in this case. So the infinite norm of any element taken from BE is given as the supremum of the modulus of such functions for all x belongs to the domain E. Okay. Now see, this is basically, we can relate this bounded case with the L infinity, right? Because see, BE is same as L infinity if E equals to n, so this becomes a set of sequences which are bounded, right? Very simple. Okay. One more example, one more fine example. Suppose we take this set C01. Okay. This is the set of all continuous functions with domain 0 to 1 and range codomain real numbers such that f is a continuous number. Okay, and it is a vector space. It is indeed a vector space. Okay. Now the norm of f, the first norm of f rather, is defined like integration 0 to 1 mod of fx dx. Okay. Okay. Got it? Clear? A norm infinity we can define as we did here. Okay. Norm infinity as the same definition. Now this definition is opt because we know every continuous function is Riemann integrable. That's why this definition is appropriate, might say, right? One more interesting proof you have in case of this first norm. I'm keeping it as an exercise. So this says that norm of f equals to 0 implies f is equals to 0. Okay. Try to prove this. Okay. The converse statement is very trivial. I'm not giving the proof of the converse statement. Try to prove this. Okay. So now we move on to some general theories related to metric spaces. Okay. So we already know. So suppose we take this as a metric space. Okay. And now say we take an element from X and we take a non-empty subset of X. Okay. We can define a distance or a metric between this element and this set. Okay. Which is given. Now see, suppose this is X. Okay. And let's say A is this region. A is having numerous points. So what must be the distance between X and A, you might say? Or rather, we define this metric. You may say the metric can be defined as the minimum of the distance. Right? But in this case, what we take into consideration is the infimum of all the distances possible. Infimum of all the metrics is possible. So infimum dxa for all x belongs such that x belongs to a belongs to this given set. Okay. If x belongs to a, then what will happen? In this case, if x belongs to, what is the infimum distance? So x with x itself, because x is an element of a, right? So in case of this, you have dx of a. Now see, I'm making you understand this one. Suppose this is a region A and this is a point X. Okay. What must be the distance between X and A? It must be the smallest distance. Right? It must be this smallest distance. That is what we have defined here as the infimum. Okay. Okay. Achha, is the converse true? Is the converse of this statement true? Let's see. Suppose you take X as 0 and you take A as the set 1, 1 over 2, 1 over 3 and so on. Okay. What is d of X? it is the infimum of x minus a. What is x? X is 0. What is the infimum of a? 0, because as its infimum to 0, it is bounded below, so it is 0. But does 0 belongs to this particular set? So the converse need not be true. Okay. Now we can, a similar way we can define a metric between two such subspaces, you will say. Okay. So, or two such metric spaces rather, two such metric spaces. Now which belong to some, or rather two subsets of metric spaces. Okay. So suppose you have xd as a metric space, and we have already taken a. We take one more b from x. So d of ab is defined as the infimum of the distance between arbitrary points of a and b. Okay. So in this case also you can use a similar diagrammatic representation. So suppose this is a and suppose this is b. So this, the minimum distance between them is defined as the metric. Okay. Clear? If a intersection b is not null, okay, there are some elements common to a and b, then what must be the minimum distance between them? It must be 0. It must be 0. Right? Is the converse true? Let's take a as 1, 1 over 3, 1 over 5 and so on. Let's take b as 1 over 2, 1 over 4 and so on. This is bounded below to 0, this is bounded below to 0. This is disjoint sets, but DAB must be 0. Bounded below to 0, bounded below to 0. The infimum of the distance between them must be 0 as well. Very simple. Okay. The next thing we have is the diameter of a subset of a metric space. Diameter of A. This is given as diam A or dia A. So it is the supremum of the metric xy such that both belongs to set A. Okay. Suppose this is A. So suppose this is say x and this is say y. This is the metric between them, let's say. So the maximum distance between them possible must be the diameter. Right? Must be the diameter. And also you might see something that this diameter is depending on this metric. Because as the metric changes, the concept of metric between x and y will also change. So diameter depends on the choice of metric. Very important. Okay. So the last definition of today's lecture is discrete metric. Discrete metric. So this metric space xd is a discrete metric space if the metric from x cross x to R is defined as d of xy equals to 0 if x equals to y and is 1 if x not equals to y. This is called the concept of discrete metric. Okay. So let this lecture be up till this much, guys. In the next lecture we will be bringing the concepts of open balls, open sets, spheres, etc. So meet you guys in the next lecture.